have switched on now the record option.
من لدرجة إن أنت غلط تعملي أكل.
Shantanu, are you ready to get started?
I am.
Terrific. Okay. Thank you, everyone, for joining today's PRACE XSEDE webinar. As some of you might know, about a year ago at this time, well, actually more than a year ago, PRACE and XSEDE have been looking at ways to support researchers who use both infrastructures, and there would be some nice things people might be able to do if they could work together in a more reliable fashion with software that interoperated a little bit better. And so 3 research teams were selected last year at about this time to really undertake some sort of pilot program at what interoperability might look like, but with science goals as well. So now, just about a year later, we're going to hear from the 3 teams about how it's been going and what they've learned along the way and what they've been able to accomplish. Our first team is led by Shantanu Jha from Rutgers University. He works also with Peter Coveney from University College London and Dieter Kranzemüller from LRZ. Shantanu, I'll probably be brief with the introductions here since we have so many speakers, but please start your presentation, and thank you to everyone else who is on the webinar for joining today.
Thank you, everybody. Before I begin, I just want to check that as I move the slides, people are able to see the movement as well.
Looks good.
Great. Thank you again. So, Nancy, Ralph, thank you all for the opportunity to, first of all, be part of this XSEDE PRACE project, and also the opportunity to present on behalf of Peter, who sends his apologies for being doubly committed at this time, not being able to join. Introduction, but the perspective I want to take for this presentation is that of cyber infrastructure and federating cyber infrastructure. The definitions of cyber infrastructure. One of the favorite definitions actually comes from Stewart. He emphasizes the importance of the people as much as the actual physical resources, and obviously the networks and the connectivity between the people and the networks and the infrastructure. This project is really about the infrastructure, the physical infrastructure, facilitating complementary sets of skills across the Atlantic, and the infrastructure serves as a nice function, but also a nice opportunity to put our respective scientific skills, if I may say so, together in sort of a common science problem. I don't think Peter needs any introduction. Peter's a world-class chemist who's spent the better part of the past 2 decades making advances in methodological approaches and for free energy calculations, amongst many other things. I've been working in the high-performance distributed computing for the past 10 years or so now. And I just do a couple of things. I just try to understand interoperability at a conceptual level. And over the past 5 years, my team and I have spent a lot of time trying to support any simulations mode of computing. Applying philosophy that I think there's a need for these ultra-mega single simulations that scale to 100,000 cores, 1 million cores. But machismo associated with those if you look at where the real science, or I should say the bulk of science is going and needed, what is needed in terms of computational capabilities, the need for supporting many simulations approach. These could be heterogeneous, these could be coupled, could be uncoupled, there could be different forms of coupling, which by some accounts some people would like to call workflows, but I'll not open that can of worms because everything is a workflow. I tell you is that the question of Peter's expertise and my team's expertise is the fact that there's a very large set of important scientific problems in general, but in particular in the area that Peter has specialized in, namely finding free energies of best biomolecular systems. And my research, which has looked at theoretical aspects and implementation aspects of how to support medications running on distributed as well as high-performance computing. What you see today is a manifestation, or I should say a snapshot of that research that has been in progress for at least 7 to 8 years. Peter and my collaboration goes back for the duration, and hopefully just the beginning of many more. An important and a critical component of which has been facilitated by this project. So I'm not speak about this very specific, too much details about this very specific problem which we've been using this project to investigate. But just to set the context, it's about HIV drug resistance and the fact that there's a mutation in the proposed, in the HIV structure, and that makes the set of drugs that are currently used and the proposed drugs susceptible to become effective very soon. Last word, think genomic revolution. There are many ways to address this problem, microbial resistance, various other kinds of resistance and mutations, but one approach to customize a cocktail of drugs to a patient's specific genomic profile. It has as many questions as it answers. Well, isn't that the purpose of good research? But one of the problems that it does open up is how do you manage many millions of simulations, possibly of being lengths, possibly of varying capabilities. So that's the full problem. Obviously, we're not solving a million simulations here, as you said. So Peter and his team over the past years have been looking for essentially an end-to-end workflow. Now, at some stage, I could wax lyrical. I could give lectures on the difference between general-purpose workflows and domain-specific workflows, and why the latter is the right way to go as opposed to the former. But this is not the time or the venue for that. What Peter has essentially done is he's created a domain-specific end-to-end workflow, which he calls BA, Binding Affinity Calculator. It's actually even I should call it problem specific. And no surprises, it's to reliably predict just give me a second, sorry, the window is, my slides are being obscured, I apologize. Right. Okay. And the goal of BAC is to be able to predict the binding affinity of these compounds without exposing any of the significant details and challenges that are inherent in the end-to-end process. I should lay out that I talk about millions, but any specific problem could have order 10,000, 20,000 different simulations, depending upon the problem being studied. Right? The scientific objective here is to be able to rank the binding affinities of various drug candidates. Okay. So now to the computational challenge, having hopefully understood the high-level scientific goals. To compute the binding affinities of these drug candidates using one very long simulation, thereby if you principles or hypothesis, time averaging over space averaging should ultimately, in the thermodynamic limit, work out to be the same. What you're seeing is almost schism in the entire biomolecular sciences community as to what is the right approach. For a given amount of computing time, should you employ a single long trajectory approach, or should you decompose long trajectory into many smaller trajectories, so essentially replicate the system with the starting points and the shorter durations? This problem, this is a question that has had similar incarnations or has had many different incarnations in many different fields. And I'd be glad to hear about other fields as well. In this community, in this biomolecular simulation space, this has acquired a particular interest. On the one, you have the people like D. Shaw, who to create special purpose machines in order to really push forward develop the state of the art in the single long simulations. And a large number of us have been trying to respectfully disagree with that approach and saying, if you think about the things carefully, well, you're going to get more bang for your buck in the other direction, namely by thinking of many larger simulations in quantity. And are very complex. It goes down to the fundamental inaccuracies in the parameterization of the field, so on and so forth. But the point is, Peter's, and we've published a paper a couple of years ago, which quite a bit of attention at the AS and elsewhere, and NSF picked that up, where he shows for the first time that if actually employ single simulations, you get exaggerated, but you fair to say uncontrolled errors, and more importantly, the result of the errors are slightly unreproducible, and we can get into the fundamental reasons for that. In our paper, we looked at when you run not a single long simulation, but you reproduce using ensemble-based approaches. And what we find is for a set of 9 drugs, the FDA-approved drugs for HIV, the errors are in control, smaller, but the results are more reproducible. So this is very interesting. I mean, if you think about it, it's really getting down to just we are doing whatever we can do computationally, but there are deep algorithmic and formalism reasons for doing what we're doing. So it's the algorithms, formalisms, and the cyber infrastructure, the software, working in tandem. The protocol employed, any good scientific experiment should have a well-defined protocol, is out here. There were 50 replicates, ensembles for the various science problems. A lot of effort into determining what's the number of replicas. Again, but the constant here in all of these experiments is the fixed amount of computing time. If you lax that, if you change that, then obviously the parameters that I lay out on this slide, 50 could soon become 100, depending upon how much computing time, or could just as well become 25. See, the other 3 parameters, the duration of the trajectory around 4 nanoseconds, as opposed to some mammoth efforts of approaching a microsecond. So again, there are details in these papers written mentioned below and in others. And the nutshell here is that the single simulation is not as reproducible. And as I say, Peter likes to be emphatic. He likes to call it unscientific. I try to take a slightly more ecumenical approach and say it's less forceful as it may have been once upon a time. So again, here's more details, death by graphs here, but the real important things are the fact that the profiles as produced by the ensemble-based approach are also more natural from a statistical physics distribution. Okay, and again, for those of you who are in this domain, you may want to see the paper referenced here with all the gory details. It's a 25-plus page. So came the starting point of our work. Some of this work was done as part of this project, but also some of the core ideas were already developed, and we've been trying to grow since. So just moving forward, and this was a BBC article and a few others that picked up the fact that supercomputers can help in a better design of drugs in the future. So I've laid the context, I've set all of this out. So what's the computational aspect? So Peter and I have been working for 7 or 8 years together. Some of you, at least I know Nancy and I talked about this back in 2005 when Peter and I won the Supercomputing HPC Analytics Award. And so I don't expect you to remember, but might remember that the problem for which Peter and I won the Analytics Award at Supercomputing was for computing this free energy profile of in this case, a polymer translocating across a nanopore, a pro-nanopore or a artificial nanopore, irrelevant at the level of detail. Very large simulation, 400,000 fully solvated, 400,000 atoms in a fully solvated system. And we spent, as a matter of fact, my one whole year of my postdoctoral research was spent in coming up with an algorithm that allowed us to not run as a single long simulation, but be able to recompute the energy profile of translocation along the axis of the for non-equilibrium simulations, and showing that you can actually recompute the equilibrium free energy profile. That's all details if you're not from this field, but basically it was establishing the algorithmic formulation that non-equilibrium simulations, in this case, many smaller simulations, had the fundamental capacity of reproducing the equilibrium property, what you get from a single long simulation. The mathematics, the algorithms, and the fact that we at that time got TeraGrid to help us make some initial progress was, I think, what impressed the supercomputing judging committee. As I like to now say, it was a big lie. Not we lied, we were never intellectually honest, but we said we've set up the problem, we've developed the algorithms, and you know what? The TeraGrid can now help solve this problem quite easily. We just have to run about 1,000 to 10,000 MPI simulations of 512 cores each. That shouldn't be too difficult, and that's what we presented. We spent the next 2 or 3 years. I moved on to the US. Adel bought this big lie. He thought we had solved the problem. He hired me at CCT, and we had a student back at UCL running these simulations. And you see 2005 to 2009, we tried to run 1,000+ MPI simulations of 112 cores each, so that he could reproduce the equilibrium free energy profile. Probably what I mentioned in the slide, it did not go off very well. It was supposed to be a quick time to solution, ended up being a highly protracted time to solution. We got the answer, and that's why you see the cover of a very important journal in chemistry. So we did, but we with a lot of grief. Asking you to calculate the scale. On the one hand, we tried to do 1,000 to a few thousand MPI simulations. It took us order of years to get that done. What I'm trying to tell you now is the kind of science that Peter's doing as part of this binding affinity calculation for FDA drug. For that very paper, we probably did at least as many simulations in 2013, 2014, and we're now doing more. What's changed? Well, one change is the availability of some fundamental abstractions, computational abstractions, that support the simulation view. Right? And again, there are lots of details here. I'm sure time is short. I just want to point out that what was earlier a single job effort, one by one, we created a set of abstractions which supported the collective execution of many jobs. And remember, these are not entirely uncoupled. They could be, but they're not entirely uncoupled. There's a simulation phase, there's an analysis phase, there's a simulation phase for the particular problem. Enter Radical Cyber Tools, the set of tools and capabilities that I've been working on for some years. And these 3 aspects that you need to know about Radical Cyber Tools. First, is there an explicit layer to the heterogeneity of infrastructure, which all know is a fundamental attribute when you use distributed cyber infrastructure of the type either external to XSEDE, i.e. micro-level heterogeneity, or at a macro level between XSEDE and PRACE. You write abstractions to manage the heterogeneity, and again, I've spent the better part of the last decade thinking of the right approaches to manage this heterogeneity. But it's a necessary condition, it's not a sufficient condition. A sufficient condition, I believe, is, along with the heterogeneity, the ability to have flexible execution and source management techniques. And my slide will be about a specific approach to this, which we call the pilot abstraction concept. And many ways to look at this. It's a lecture or several lectures unto themselves, but the primary aspect here is that you have a container job, which then becomes a container for the largest, smaller simulations, and have control over the execution, the resource assignment to the any smaller simulations, which is highly non-trivial. The important part is that these components, the heterogeneity layer, the resource management layer, they are solutions unto themselves. They be extensible accessible and usable by higher tools, higher level libraries, so forth. So one that in as a fundamental design consideration, the landscape changes. You're now thinking of programmable building blocks or external building blocks, and where the coupling with Peter's back comes in. The marriage of the binding affinity calculator with radical cyber tools is what is known as HT-back, high throughput binding affinity calculator. Using this combined capability, we've run the back, which earlier was not able to run on a broader set of resource infrastructures, and illustrate just a few here. Arch Superbook, thanks to Dieter and Helmut, and obviously all the XSEDE resources. I like to call this as saying it is the match of two appropriate capabilities, using interoperability for free and more flexible resource utilization modes. So here's a landscape of the three important components. At the top, you're back. At the very bottom in yellow, you have the Saga layer, and in the middle, you have what is the resource management layer, but specific incarnation of which is the pilot abstraction. I will bore you with Saga and the Python implementation coming from my group, but just remind everybody that it's a standard. And I have a joke in my group, which I call Radical's First Law. It grows to start developing adapters for different heterogeneous infrastructure. Think of the phenomenal waste of time and human resources, and NSF should, I'd say, ban any project that claims to write another adapter for another infrastructure. Because by the way, this has been done, and it's been done in a standard form. Yet people continue to do that, so I will not begin that battle. Just want to say that at least 4 or 5 different years, a dozen groups solve this problem, and the problem has a name. The solution to that problem has a name called Saga. Let me just speak very quickly to the pilot layer. Again, there are 20 different pilot jobs out there. Everyone spun up on their own for a very specific reason, for a very specific infrastructure, for a very specific usage mode. For the 3 or 4 years, we've been sitting down, analyzing these 20 different pilot jobs, trying to find a common minimum model for pilot jobs, because pilot jobs mean different things to different people. The result is a theoretical model of what constitutes a pilot job and what does not constitute a pilot job, but that's called the P-star model, and there's more to it. And the implementation of the P-star, a reference implementation of the P-star model, just like there's a reference implementation of Saga, is called the radical pilot. Some of you may know the earlier incarnation, big job. You would think the number of not inappropriate jokes associated with the name, so we thought we'd give it a slightly more revolutionary name, hence radical pilot. And to heterogeneity, and it's important to appreciate heterogeneity, especially in the interoperable context of this project, it manifests at many different levels and different dimensions. One particular approach that requires addressing is the Saga, the access layer heterogeneity, but at some level you also have to counter the level architectural heterogeneity. This is just a long-winded way. I will not get into the details of the slide, of that some of the heterogeneity also has to be handled by the pilot layer, and our architecture of the pilot layer considers the fundamental changes that you encounter or differences you encounter going from machine to machine, and that is those changes are localized in what is known as the pilot agent. Again, a structured approach, scientific approach to managing the heterogeneity, yet not losing some of the performance and flexibility that is needed. Again, another lecture. So why the focus on pilot jobs? Well, there's a lot of reasons for using resource and managing resources flexibly. If there's one thing that distinguishes high-performance computing from the multi-site high-performance computing is the fact that the traditional high-performance applications, your monolithic MPI jobs, they have a static mode of utilizing resources. You ask for 100,000 cores, you use that for the entire lifetime of the project. You typically divide, slice, and dice that between different tasks. The evolutions of MPI will obviously address this, but as of today, that is not state of play. And in high-performance distributed computing, what we're talking about in this many simulation mode approach is the ability to have a final level of control. Now, people say, why don't you just stop trying to do the pilot job things? Just ask for the right amount of cause in the first place. Well, we have papers out there which do that, predicting the availability of a particular size is fundamentally a futile task. The process is chaotic, and I do not do chaotic in a light-hearted way. I use chaotic in a technical sense. I extreme sensitivity to initial conditions, and so the attempt at actually using predictors to profile your jobs to run quickly, by definition, doomed at the start. And if you can't beat the process, you cannot actually start predicting the right resource profile. Well, the right thing is to be dynamic adaptive. Hence the focus on pilot jobs, the right action for the right scientific problem. And then the pilot action provides a very simple but elegant unification of HPC, HTC, DCI, and high performance. And so makes redundant this nonsensical debate that goes on in the community. Is it HPC or is it HTC? Is it distributed or is it parallel computing? The wrong set of arguments. Here's an abstraction that renders all those arguments irrelevant. And third, but very importantly, it's a building block. It's used by many different layers, high, above, and back is just one example, several other examples. So the status is we're deep in the trenches going on, making hopefully scientific core conceptual and formalism advances in the domain of biomolecular simulations, bringing and that happen as a consequence of deep research in computer science and cyber infrastructure. And this has been ongoing, is ongoing, and will continue to be something that occupies our time and energy. And this is all possible thanks to all our respective teams, but so also thanks to Nancy and the XSEDE team for making allocations available on XSEDE. In particular, also to Dieter and Helmut for helping short-circuit some of the bureaucratic processes at PRACE and providing us with a very quick allocation of 1 million views on Facebook. And I am completely missed in omitting Mark Parsons, who also provided a special allocation on Archer, along with Dieter on Supermook. And obviously use our regular set of allocations to use a very, very large heterogeneous set of resources, ranging from Archer, Hector, Supermook, regular XSEDE resources, to non-XSEDE and non-PRACE resources. You will know of the world-class Hartree Center that's upcoming, that's up and coming in Britain, which has access to BlueGene. So our work is a combines not only XSEDE and PRACE resources, but all the BlueGene machines at the Hartree Center. With that, I'd say thank you very much for your time and attention. I'd be glad to answer any questions.
Thanks very much. Do you have any quick questions for Shantanu? I see that the attendance list has been growing steadily during your talk, so that's probably due to the sun rising here in the U.S. I had a question if no one else wants to jump in just yet. So you've been doing large-scale distributed computing for some time, Shantanu. I wonder if there was anything different about your experience this time, anything that was better or worse, or kind of how have things changed since that 2005 experience on the TerraGrid?
Nancy, great question, and I think it gets to the heart of, whereas I say things are still hard, but there is definitely a measure of progress at every level. If anything, has only increased over the years, and therefore, if not tackled properly, have potential for becoming a more difficult problem and possibly showstopper. But thanks to sustained effort over the years, we've learned how to manage the heterogeneity, and not just manage it in the sense to know how to respond to it, but also how to build the heterogeneity. There's a one quote, managing complexity is not the same as exposing simplicity. And what I think we've managed to do is do a bit of both. We've enabled Peter and his team to see the structure in the simple way, with the simple model, conceptual model, as they want to. Yet, we've localized the management of the heterogeneity and complexity into one or two well-defined layers, and we have experts handling the heterogeneity. So, along with saying, Nancy, that the columns remain, but are of heterogeneity, which, as we discussed, is a fundamental feature of high-performance distributed cyber infrastructure, but we better how to manage it and not have it permeate across all layers. So in that way, the experience, at least for Peter's group, has been way better thanks to the right abstractions. And also for a group, we know how to manage that and keep it localized. I hope that answers your question.
Yes, thank you. That's good to hear. Any other questions for Shantanu from folks on the line?
Yes, Shantanu, Jules speaking. I'm especially interested in your experience working between XSEDE and PRACE sites. Did you really use communication between XSEDE sites and PRACE sites, and what has been your experience with that?
When communication, do you mean communicating with people on either side?
No. From your pilot jobs, did you run the jobs between the different resources?
Yes. So let's be careful. This is not one pilot job running across XSEDE and PRACE resources. No, a pilot is confined to one machine. And it runs that machine. And then
but what I understood is that you manage it from another piece, or?
Yes, that's why it's distributed computing. We sit on a laptop, which could be at Rutgers, could be at London, wherever, and London emits to XSEDE machines as well as to PRACE machines without actually physically having to log into those machines.
But you don't need specific network communication between sites. You don't have large requirements in that respect.
Absolutely correct.
Yeah.
Thank you, Jules.
Good question, Jules. I know XSEDE is starting to look at some software-defined networking options in the coming years. I don't think we have schedulable networking today, but that would be something interesting to think about across the sites. Any questions for Shantanu? I wanted to note, too, that Tabitha Sale has joined. Tabitha was our lead XSEDE support for this project and is also going to be speaking the contribution of the speakers today for XSEDE 15 this summer. Morris, do you want to go ahead and load your slides? I can do a desktop. Oh, there we go.
This one on? Question. Someone from the audience hear me?
Yes, we can. The slides look very good also.
Great.
Morris Riedel, is that how you pronounce your last name?
Thank you.
Probably. From Ulick will be our next speaker. Morris is going to be speaking to us about his PRACE XSEDE collaboration, which involves large-scale Earth science data. I see that some of it's also being presented at the Research Data Alliance meeting here in San Diego next week. Are you going to be here for that, Morris, or is someone else presenting that?
One of the authors of this work, Marcus Götz, will be there next week. I can't, unfortunately.
Okay, I'll be there and I'll look for that also.
You can meet Marcus. Let's see.
Good. Why don't you go ahead?
I would invite you to come to the RDA Big Data Analytics session. It will be interesting. I think it has quite some overlaps with processing needs in PRACE or XSEDE.
Good. I'll look out for that one. Thank you. With that, I'll let you get started on your talk since we have also Sandra Stefan, and I want to make sure everyone has time.
Okay, thank you very much for the opportunity. In contrast to my previous speaker, Shantanu, we are much more on the data side. So what we actually were exploring were the term data analytics analytics, and with this, what kind of technologies are there or are required to perform data analysis, or recently also known as data analysis or analytics across XSEDE and PRACE. We talk more. Let me just say a few thanks also to some of them that I didn't put here on the slides. So you see some of my PhD students, but also I would like to thank some work that was included of bringing parts of it on the Blue Gene Queue, which is Michael Stefan, Michael from the Unicore team, so there are definitely more. That's why I put et al. Here. Andrew Grimshaw was here as a visiting scientist and installing and helping us with GFFS on the Blue Gene Queue. So there's much more to this, and I have an acknowledgement slide. It's just not possible to put all of them here in front. Anyway, one form or another, those that are here on the front will not also present. So Shabbos is with me and will take over the second part, which is then more technically on one specific solution. So let's to the outline that we thought would be very interesting for the audience. First of all, everything we do should be motivated by a scientific case that we outline and that we had in the project proposal. If you read this, it was mostly focused around the earth sciences domain. We also do neuroscience studies. This is particularly the one we tried for several small projects, I would like to say, in terms of technology assessment, in terms of really figuring out what is the price we pay basically to go away from the numerical simulations that we know decade, more data intensive work. So looking at R, looking at different existing technologies and how they could, say, more obviously support big data analytics frameworks and what's actually out there. So I'm getting it is that we have lots of results in terms of technology assessment, and that's what we promised. You see a quote here from our proposal. So then we really didn't ask for resource allocation or something, so we actually don't needed any runs or so. For it was much more a point of, are the configurations that are required for data-intensive science? What type of technologies exist, and also with the paradigms, right? So if some of you recall, you cannot easily bring a MapReduce job on MPI. All the frameworks often promise that MapReduce jobs, for instance, solve a lot of data-intensive science problems. So a lot of technologies we investigated, and we picked one particular problem. We basically note as a scientific case and provide a solution. We also compare with the existing solutions here that's ready to use now. So everything we have here in place can be used over standards and the interoperability that exists in XSEDE and PRACE right now. Here and there, things need to be configured, and that's what we will explain in the talk. Some solutions, again, the point, the technology is there, but of course, if you would like to be using it, you have to have resource allocation. So everybody here on the webinar or later on looking at this should be aware of, you can theoretically do this, but of course you have to get grant allocations in PRACE or XSEDE to get calculations done. We would like to start with scientific cases, and we put 5 in this project. I will quickly go through while focusing on one. So in the Marcos case, this is basically data coming from different aircraft, where we largely looked into how well supported is R across the infrastructures. And we found, while discussing with many sites, that R is typically quite well supported, and this is what you, for instance, use in this particular case study. Then go to the events part, which was, let's say, more event tracking across different geolocations like storms and so on. We found that there's a specific requirement to use something like we call array databases, not traditionally supported in XSEDE and PRACE. So we figured out and basically tried to install that and evaluated this, how this could be, let's say, put an HPC environment like XSEDE and PRACE, and found out that this is actually not that simple. So it requires root writes, it requires workarounds. So it's a technology which requires much more investigation if PRACE or XSEDE would like to use these kind of technologies. Another one we just recently invited was Rasterman, where we also looked into, it's another array database, but it's very suitable for geolocation data sets. And seismic activities, as in the The last one that we have with the information systems, also from the geosciences, we looked at small frameworks, quite feasible. For instance, the GIS system has a scientific gateway, which is very promising, provided by Xiaowen Wang. And as far as I know, this is already on the track towards XSEDE. So there's someone to go ahead with this, and with this you could use different infrastructures. So all of these different projects basically have some results in one way or another in terms of technology assessment. But here on the webinar, we would like to focus on one, and this is this Pangaea lighthouse that we call it. And it's a problem that you see on the left-hand side. Basically, there's a huge open collection of data sets. And the line of open data sciences will be expanding significantly in the next years. You see quite the graph increasing right exponentially in the last couple of years, and it will basically follow. And that's the term where we're starting with data. But it's not only about the volume, right? So it's also about the different variety that we have. You see that on the bottom with different profiles, seabed photos, air photos, outer records. Here in particular in this webinar, again, we would like to focus to have a concrete solution here for a problem, and the time series analysis that we would like to show some possible, let's say, frameworks and algorithms that solve this problem. So this is this particular one that we picked out of these 5 to show here. In the paper we would write possibly more, but given the time constraints, I really focus here on this one. And the data problem is given by the situation that there is an autonomous measurement device basically everywhere. It's in the air, in the ocean, there's a cabled observatory in the Korea Fjord, so there's lots of data collected. And in the past, more and more scientists have looked at this and did manual quality control and the search for interesting events, of course, and anomalies. But this is becoming more and more difficult. So there is a scientific case here that this needs to be automated, right? You can do outlier detection with simple plot studies, but if you have big data growing and growing in the next years, this is not only a problem for the Korea Fjords in Sweden, but notably for the whole Pangaea open data collection. And that's why we created this case, looking at some, let's say, more automated ways or semi-automated ways, how you can actually detect outliers in this data. And in particular here we have time series measurements basically in the Korea Fjords. And this now basically can XSEDE or PRACE in terms of technology provided in order to solve this problem. So these instruments, of course, basically published in other work or so already in last year, where we have some results at the EGU, which is the European Geosciences Union 2014 conference, where we had initial studies. This brings us to the discussion and to the point why we need a DB-scan algorithm. So this is a typical clustering algorithm, as we would call that in data mining. One of it, which is really strong compared, for instance, to K-means clustering. It's called density-based spatial clustering of applications with noise, hence abbreviations DB-scan. And it's a quite old algorithm, if you want, from 1996, introduced by Martin Ester, and it groups numbers of similar points, as you can see on the right-hand side, together. And different distant measures you can use, like for instance the Euclidean ruler distance, as we would call this. And you can see on the right-hand side what it does to your data. It takes, let's say, unlabeled, uncluttered data and gives them a meaning, groups the data, and this density measure, for instance, Euclidean. And the interesting side effect that this algorithm or this particular algorithm has is that it's not only able to work with a large number of clusters, it identifies outliers and noise, for instance, in this time series that we have in Pangaea, for example, as noise. This is a very critical part why we choose this algorithm in order to fix that problem. So this is our technical requirement, scientific case study. But I look now basically more in the literature how it works. Of course, there's a bottleneck that lots of these data must be in memory. So this is the first constraint. And also think about the time series we're facing. We even go for 10 years or 20 years time studies, where of course this all will not fit in memory. Hence, the part for a parallel scalable application of the algorithm comes into mind. And another part that we would like to particularly focus here in that contribution is that it's very critical to find the right parameters with it. So there are two parameters called epsilon and min points, which basically can see on the smaller graphs, hard to see. Let me just explain it here a little bit more broader, where epsilon is the kind of circle or disk where you basically have a number of minimum points at least to form a cluster. So you can see it as two constraints, but finding these two parameters is easy. Right? You need to do parameter sweep studies in order to find the right ones. And in particular, this is a drawback of the DB-scan algorithm, partly that with changing time series or with changing densities, you always have to adjust the parameters on the fly. So if you have a real-time problem like the time series, you really have to have lots of these parameters in parallel fit on your data in order to see whether your parameters are actually right to solve the problem. So now note that we have two different things. We have on the one hand side quite some parameters we have to adjust and submit often. And on the other side, we also have parallel and scalable needs because the data set will not fit in one particular system of small size. Hence our technology assessment. And this was quite, let's say, surprising because many of the frameworks we looked at were the ones typically referred to as the MapReduce ones or high throughput computing ones. We're starting off Apache Mahout, a very famous machine learning framework on Hadoop base, which does not offer any DB-scan implementation. And more surprisingly, also the Apache Spark machine learning library, just recently being more and more momentum in the data mining and machine learning community, is really not supporting the parallelization of that. We include Python because Python more or less has quite some momentum also in scientific communities, but also there is no parallelization strategy for DB-scan. Of course, out here usual serial tools like R or RETL, Pika, MATLAB, and so on. If you load some of the data sets in the time series, you most probably get a big problem anyway. The only ones that were applicable to the PRACE and XSEDE environments in our technology survey, we published this and basically, or we submitted this to a data mining for conference for more information. Please feel free to contact us. Just two you see here highlighted, which is one that we created ourselves. With ourselves, I mean one of my talented, or two of talented PhD students, and basically compare them with the existing MPI implementation Northwestern University provided. Let's address a little bit the parallelization results. So this is really how we scale to the order of magnitudes we would get from the time series. So we had a very smart big data pre-processing in terms of different cells. So you combine the kind of density-based clustering here with grid-based clustering. There are also ones like hierarchical and so on clustering methods that are there, but here we have a kind of hybrid of two different approaches, which makes this scale. The implementation is free available. OP and MPI can be used together as a hybrid application. We have different pre-processing steps that you can see on the spatial grids. We don't even necessarily require adaptive mesh refinements like used in the numerical situations use cases. And we have some optimizations in place where I cannot go into for time reasons. But then you see the references. There's a very nice web page where you see all the details about this particular tool we found most notably useful. And it's one of the key results here from our technology assessment. And with this tool, given the allocations in the future, we are very, I think, looking forward to the time series issues. So when you compare this with the comparison of the existing runs we had from the Northwestern University, see very quickly that we have a nice speed up here on the right-hand side. But we don't use necessarily big cores, which is another finding, right? In data mining, we're not filling a full bloom gene queue. We here in this speed plot, for instance, using 512 cores. But always consider that this is just one data mining run with one parameter setup. So if you think about what I said before, finding the right parameters in that sense, it can be really a tough issue, and then requiring lots of different parallel runs or number runs. I think Chantino called them replicas, something like this, basically lots of them in parallel. But more notably, you see on the right-hand side also the low memory usage that we basically have here when you compare to the other implementation. We have used so far with some applications as a proof of concept. Again, we don't have the big allocations yet, but this will probably something as part of the PhD study with the Pangaea dataset in the future. And quite much works out, so we are very confident that it will also scale to the large Pangaea Earth science data collection. You see a point cloud, which is another clustering problem. We used it with all the data is available on the u.b2share, where you can, let's say, use the data. The same is true for Twitter. We uploaded the Twitter data, where you can basically reproduce the results, which is another interesting aspect here of these findings. And let me point out that this algorithm implementation is free. The implementation is free, open source, and if you want to work with us on this, please give us a hint. Let's come to the second problem, right? We're scalable and parallel. That's what we kind of solve with this tool. What is more important in the parameter studies, where we will later see how XSEDE and PRACE will solve this in an interoperable way. So we see here these two parameters. When you want to use it in a typical, let's say, job script, you have some dependencies like HDF, which is a parallel I/O framework, and you just pick two parameters which are related to this and always have to change. And here you see a real run, basically, that is performed here on just on a supercomputing environment with different types of data volumes, which in the data mining field already quite interesting from the terms of volume. Again, if you think about that, you had to multiply this with all the number of parameters. And the output results are typically written in the input. Hence, what you normally do is, of course, you mark each point while you sweep through the data set with this kind of notion of the density. Also will basically give not only the number of cluster, you will each point assign a label to which cluster it belongs. So the output and the input are the same data. So you have to always copy this. And do this with much more runs. You quickly come to the point that it is very tricky to work with all the data inputs and outputs. But more importantly, for our given application domain problem, while the cluster is basically sweeping through these different points here, it will also mark those as noise which are not fulfilling the minimum points requirement. And this we have outliers. Now you can easily foresee that a time series would be equally possible when you plot a graph with a series, and there would be outliers which are extraordinarily far away from the normal distribution that you have. So let's sum up a little bit what I talked about. So the main challenges we really had when using this, and again, lots of these things are uploaded where you can reproduce it to yourself on your system. You will find out that changing the different parameters, but we're using the job scripts again and again and change them for different orders of CPUs that use different resources, right? We tried Mason now, we tried Judge, we tried different resources everywhere with different skills. So you always have to have different job scripts as well, which is quite annoying. Then you usually have various dependencies on multiple versions from the implementations like GCC, HDF, which you need in a particular C++ installation. So hence you see the configuration issues you're faced as a data miner when you want to just use it. You see some module loads here in front where typical data mining from my faculty in Iceland, for instance, working with me would be never knowing and basically don't want to waste time with. Then when you're finding the right parameters, min points and epsilon, but you quickly see there are some other parameters you also have to think about, like most notably the data in and the data out. Working with this data locations is quite, let's say, tricky. So all these are challenges we pose now at the point of saying, well, XSEDE and PRACE has technology to actually engage in this. And with this, I would like to hand over one of the research scientists in my research group, which is actually working on this particular field, who is Shaba Simon, and will tell us a little bit about how we address the challenges of this.
Thank you, Maurice. Hi, everybody. We took this challenge from application scientists, and to relieve application scientists to generally edit the job scripts and also compare applications on different platforms, and also doing and sending jobs, submitting jobs on different resources with different parameters. So we were discussing at one point that why not we just use a middleware solution and use a standardized protocol so that multi-resources, different architectures or infrastructures can be accessed in a very seamless and what we say unified manner. Considering XSEDE architecture, so on the right side you see an XSEDE architecture with a lot of elements. So we specifically focused and took the action management part, and we analyzed that the standards are really viable solution to actually automate the process of solving this DB scan algorithm across different sites, like job runs on different sites. So, and we took the common protocols that are actually deployed on XSEDE and PRACE at the same time. So in XSEDE and PRACE, the most common standards and implementations we have available from OXA Basic Execution Service, which is OGF standard, provides services a SOAP-based, web-based interface for managing and monitoring jobs. As far as interfaces are concerned, these are the major interfaces that are used to manage and monitor the singular and, like say, multiple jobs at once. As far as the job request model is concerned, we use the job submission and description language, which is a very common and well-adopted standard to specify the job requirements while submitting or ending with the batch system via middleware. So, and not only JSTL as a pure specification, we took a lot of profiles. It has a lot of helpful profiles and extensions like HPC profile, HPC High Performance Computing Basic Profile. Most importantly, parameter sweep, which is a very useful extension in this case for solving data miners' problem of run multiple jobs in one request. So you can specify a formula in JSTL that sweep across multiple parameters in one go. And implementation dependent. How do you want to implement it? That you want to run multiple jobs on system, or you want to model this request in one job which has multiple runs inside this one contained and composite job. And third, we used SPMD, which is a single program multiple data, that is actually more specific towards specifying or expressing requirements with respect to parallel applications. For example, MPI environments, or the variables that are required for MPI environments, like, for example, number of processes, thresh processes, etc. In this case, we, by using these standards, we use these cases of manual edits of jobs, job scripts, because middleware has all the configuration. It actually incarnates the job according to the platform or according to the implementation, the realization of the architecture. And so finding the right parameters like min points and epsilons in terms of this application. So I would rather also emphasize that this will not only help this application, it can also help other applications. We have other applications on the roadmap that will also benefit from this standards-based suite of available specifications. Now to the problem of working with locations of distributed data inputs and outputs. So we used a technology from XSEDE. It's called the Global Federated File System, created by Genesis team. So and this was the solution that we used to automate the process of data hosting and data storage and data transfers as well. So we have data in some kind of a, I would not say, maybe it's still say data cloud, but it's kind of a data file system which is globalized across XSEDE PRACE. So we have one installation and PRACE as well. I think at UQueen we have one endpoint of GFFS, so that we can place the data anywhere in GFFS and can be accessed by any XSEDE resource without any issues, as long as proper security setup is available. So now we see the actualization of the request. So how we express the request in JCL using this extension. So it's only what we say a unit job. It's not a pattern job. So you can see all the application with a lot of parameters, and all the environment settings are actually hidden. So this is the middleware job and middleware responsibility to incarnate this job and run it on any platform which has this configuration of application, or which has proper configured MPI platform with this implementation. So yes.
Okay, this is Nancy. I was just wondering, I think to Florian also, does the webinar, does it have a hard stop at a half hour past? 30?
You have to stop.
Hurry up, yes. So
I just want to make sure Sandra has time in case the webinar quits in
No, this is no problem. The webinar will continue this, but of course we have to keep a little bit the schedule.
Yes. Yep. Okay, thank you.
We will not be kicked out then.
Sorry. Thanks that we are hosts. So these are if you see in the slide, these are the parameters that we want to sweep across in different in applications in different domains. So you see at the bottom how the application will look like if there are multiple runs. So you have TV scan -e with different values across multiple min points and multiple epsilons, or what we say set density or set radius of the points in the density base cluster. So, and this is the proper realization of that how we represent this requirement in a flow uses parameter sweep extension of JSDL. So we wanted to sweep the epsilon and the fourth argument of this application across from 280 to 320, for example, with step 10. And so similar to the case with the min points. So you see that how simplified it is for the user. For example, I would user maybe for a client user interface that actually creates JSDL, generates this JSDL, can easily simplify the problem of a data mining expert. He can specify, represent an abstract job with opposite in nature. So next slide. And this is the middleware implementation, or what we say deployment perspective, how we performed initial runs, because we just started these runs on both sites, so Blacklight in Pittsburgh and Judge. So I think Jason is on the way on the deployment, so it's under progress. So we used client desktop provided Genesis to middleware, and for GFFS implementation, we use deployment from XSEDE, which is like ubiquitous across XSEDE and some of the, I would say, one PRACE site. And these, for the job runs, we are using the standards-based protocol to express the job requirements and the job requests. So you see this how one client can access and can make multiple runs to analyze the application and data sets across different architectures and different infrastructures as well. So this is what we say, just to show you the snapshot of how the results like through the GUI interface provided by Genesis 2. So you see out just a visualization of the application output that I think Maurice also showed you, that you have set of clusters and resultant output showed through the GUI interface by user, like XSEDE user, for example. I wanted to also mention one more thing, that for accessing the resources, we used my proxy service provided by XSEDE, so that users from XSEDE who has the XSEDE account can easily run jobs across both infrastructures. Thanks to my proxy and the architecture experts in XSEDE. Now I'd like to conclude on behalf of Maurice and me. So what we presented so far is a scalable and parallel DB-scan algorithm with different implementations. We had already some implementations from MapReduce and from Northwestern University that we found that are not scalable, or either they have very unfriendly license. That created new implementation in-house. This is parallelized implementation with very less code, I would say, and very less set of requirements in terms of ability. I would say. So this is our implementation, a contribution from Yulish, and XSEDE and PRACE interoperability. We thought it's helpful to use the common standard-based common standards that are available in both XSEDE and PRACE projects. We raise the parametric nature jobs and also utilize the tools that are available on these resources. So thanks to also PRACE team who helped us deploy the application and also enabling us access through Unicore to those endpoints. So next step, we like to follow this approach, and we want to automate the application access and usability of support vector machines implementation. We have another application in the backlog. It's actually also dealing with some use case with the earth sciences and the remote sensing area. And, so we also considering to apply for resource allocation calls for XSEDE and PRACE, and also in the upcoming RD and EGU sessions, we'll have this our application and implementation. I'd like to present it as well. So finally, I'll thank Robert and Andre from Bremen, and Derek J. Scott from Pittsburgh Supercomputing Center, and also XSEDE operations like, for example, Tabitha and Victor for allowing us to use these resources without any hitches, and also providing Unicore endpoints. And to Unicore team, the Unicore core development team, and PRACE and XSEDE staff. So, other questions? So you are welcome.
Shabaris, thank you very much for a fascinating talk. Do we have any quick questions while Sandra is staging her slides?
Yes.
I had a couple of things. Sorry, go ahead.
Yeah, I have a question, Morris and Shabazz, about GFFS. What is your experience with the performance? I mean, did you really share it between Pittsburgh and Jülich, or locally? That was not so clear for me.
Yes. So it was actually it was accessed by both the endpoints, the Blacklight and also Judge. So only requirement was for us to install the extension package of Unicore and Genesis, and to install the Genesis client. So it was the requirement by both the endpoints Blacklight and also Judge, and through the extension, both the endpoints can access this GFFS file system, as the user is known to the GFS server and also.
Yes, of course. And what about the performance? Did you?
Yeah, performance. I actually am not the member of the GFFS. I wanted to use the technologies, and I'm also not a promoter and not a developer of this technology. So I leave it to the Genesis 2 team, so you can communicate with Genesis on further performance-related issues.
But you didn't.
Performance was not necessarily our major goal, but still we had the Bremen data, and this worked okay.
That was my question, basically. Did you experience any problems using GFFS? I mean, how do you
we used, of course, big data in that sense, right? So
okay.
We had normal data sharing.
So the data intensity, the magnitude of data we used was 2 GB for the job. So it was okay. The performance was fine. So efficient in like transferring data back and forth in jobs.
Well, let's say for us it's fine, but of course we would recommend some more evaluation studies in detail on this particular issue, maybe. Right.
Yeah.
The point was that we can also use grid FTP as an alternative solution, enabling file transfers. So both can be used seamlessly in Unicore.
Yeah, I also note while Andrew was here and we had this installation with Michael Stefan, who is in charge of the Blue G here, we had also discussion with Thomas Eickermann, and we looked deeply more into the security, because that was more where we have been concerned with the fuse driver and lots of things which normally are also not let's say standard here. And all this was also marked as green as far as I had from the discussion. So everything was okay and in line, so that we can really European supercomputing operates that, right? While there have been other issues with scientific gateways and group accounts, the FFS technology seems to be in line with security regulations here. They're much more our focus than performance, to be honest.
But equally important, of course.
Okay, thank you very much. Let's switch over to Sandra's slides now, please. There were a couple of things that I'll have to follow up with you later on, Morris and Shabazz. I was really interested in the availability of the code that you wrote, HPDB scan. It's open source and already tuned for these architectures for data analytics from multiple domains. I think that's something we're really interested in XSEDE, and I'd be interested in how we can get that kind of installed and advertised. Alan
We
Hill,
would
I think
also be helpful in doing this, so would be quite interested to take us up in XSEDE and PRACE.
Yeah, terrific.
Have a follow-up.
Terrific. Sounds good. I see that Alan Sill is on the call, so I'm sure he was happy to hear about how the existence of standards contribute to the ease of use for this project. And Jim Basney was on and has since dropped off, the MyProxy developer. So I think several folks on interested in components of the work. I had some GFFS questions as well. I'll follow up later on all of those things. But terrific talk. Really, really interesting to hear that the code can be applied to Earth Sciences data, sensor data, Twitter feeds, also, and be so kind of flexible for different domains. Sandra, I assume being promoted to a presenter, yes. Muted. Guessing is from the University of Notre Dame. Her project involved also the use of Unicore and the Science Gateway MOSGrid, which is a chemistry gateway that's been in operation for some years now. It's great, Sandra's unmuted. We can't see slides yet.
It's work in between. So hear me now. Nice. Okay. So I share screen. That should.
You're coming up now. Very good. Thank you.
Yes. We see the slide.
Now the full screen, I hope. Okay.
Very good.
Many thanks for the opportunity for the project and for this course. The research focuses on science gateways, bioinformatics applications specifically, and workflows in distributed systems, and make them really usable for end users, especially in groups like biologists, chemists, which are not really often IT specialists, but don't have to. I mean, if you would send me to a wet lab, I would have a problem to do the experiment. So that's a good collaboration always. And I'm now for 1.5 years in the US. And in contrast to my speakers before, I don't have really a team at the moment. Hope from the mid of this year that thing works out, the grant are adapted, and but fantastic fruitful collaboration. So I would like to thank directly the MOSGrid team who contributed to this work, and the developer and his team of the PyCon GPU code. That's the code for plasma physics. And Cybers and the Airflow are European projects, and they're using WSP grade as underlying technology, and they helped also with setting up. And of course, I would like to thank XSEDE and PRACE teams and people I have direct contact often with to accomplish this project. So two use cases chosen for the PRACE XSEDE project. One is targeting the molecular simulation community, the MOSGrid Science Gateway. The project started in 2009 and continued via EU projects and via the XSEDE startup. And the PyCon GPU is targeting the computational radiation physics community, implementation of the particle in-cell algorithm in plasma physics. And the main idea is to simulate first what is measured, so help to set up experiments. And that it's especially interesting that we have the international communities already existing, the collaborations to apply for this project. So that's on the one side MOSGRID, which is a German instance with some European affiliations and international collaborations. For example, in MOSGRID we have the problem that we have German resources behind it yet. We would love to have more resources behind. It's with authentication and which certificates are allowed, so we have to deal with that. And with Cybers, we had the chance to use more resources internationally, also the airflow with the different communities in there, and ComGem. And on the US side, we are working, Notre Dame is a group, and at the University of Cincinnati. For the radiation physics code that was developed at the Helmholtz Centrum in Dresden, and there's really very international collaborations in Europe with Extreme Infrastructure, the XSEDE project, and a couple of in Europe and in the US. So I'll start the MOSGRID use case. There are three domains, that is quantum chemistry, molecular dynamics, and using different codes there, like Gaussian and WChem, GROMACS, CATSREAD. And WChem and GROMACS, for example, are both available in XSEDE, the Unicore resources. GROMACS is also available on PRACE resources. Gaussian, I've seen that it's also available on some resources in XSEDE at least. But yeah, I have still to find out what are the licenses which users can really use it, because we had that problem in Germany, and that we couldn't offer it to every user, international user who was affiliated with a German institute. And jobs are compute and data intensive. So the three research domains are quite different from each other. They are all on molecular simulation. Some of the docking, for example, you can split the data very nicely via different infrastructures. It's embarrassingly parallel, and then you can start the jobs and start it on XSEDE resources or PRACE resources and get that back. GROM, for example, has also an MPI version and a GPU version we can use. So the goal of the MOSGRID Science Gateway was always to share workflows, also to have meta workflows that users don't have to put a workflow together from scratch. If they have these mini workflows, they know that it's designed for a specific use case. We have distributed data, and of course want the users to share all the knowledge. So the experience and in the MOSGRID community, they like to share workflows. 90% of them would share workflows, and 70% would share even their data after they have published it or they have a patent. So fantastic, because we want to have this platform to really that the user communities can benefit from each other and don't repeat experiments or can start with data they get from other collaborators on experiments. In the MOSGRID instance in Germany, we work with Unite XtremeFS. I'd like to continue working with Unicore because we use some nice features of Unicore directly in the Science Gateway. XtremeFS is distributed data management system, and we are also using it still in the German instance, but would like to go in XSEDE to IRAS. So for all these points, for national collaborations, we need international resources with a single point of entry. We are using X509 user certificates and SAML, minimize the credential data transfers, because we offer in the portal that a certificate can, iPraxis certificate can be changed to a SAML assertion or created from it. Have the advantages SAML has with the maximum hops for delegation. So that means that you can set up the hops are only allowed, and if someone tries to use the SAML assertion maybe and has out that he's really a user, he's not able to use it more than for a count of a certain number of hops. And you will for different single sign-on infrastructure. That was the decision why we did this already for the German instance, but we are using it now also for the XSEDE PRACE instance. A nice feature for the users to use Unicore is they see in the port directly to which resources they can connect without that they have to sort out which resources are available, and then they can get a list of all tools they have available at that point of time, and they can put together their workflows without they have to upload something. Of course, tools have to be installed on the resources, and they have to be integrated in the incarnation database of Unicore. In Mockbit, we have the 3 domains, as I mentioned, and we are working with workflows, but also with portlets directly and created for the end users, so they can set up a job with certain parameters which are pre-configured. They can change it, but it's pre-configured for the resources, so that it's guess of the optimal that they can use, and visualization for each of the domains. This is for molecular dynamics. We heard a little bit about molecular dynamics before already from the speakers before, and the goal is always to minimize the energy to get to the most natural simulation of molecular structure. And we are mainly focusing on evaluation of the receptor interactions, special drug design. For the visualization, you see here still it's shown in JMO, so we have done quite a few portlets with ChemDoodle to show to show the structures nicely, and Mockbit is another possibility. With WebGL, both technologies, and HTML5, and users can create visualizations and have the feature then to download them also for publication. So the Mockbit XSEDE PRACE project was to really the access to XSEDE PRACE Unicore resources and get same features we have already in the German instance. So one part, of course, then the security with the certificates and SAML assertions we had to extend, and the distributed data management is still relying on XStreamFS, so that's ongoing work that we want to apply IRAS. And we see that I've shown the list of tools that users are really able to put everything together without the situation that the job is started on a resource where software is not installed, or that their workflows cannot be created or submitted because it's not in the background available. so the challenges were that we changed authentication, the XSEDE account for the Mosquit Science Gateway. We want to process the meta workflows. Setting of meta workflows, with the meta workflows means that already contract for a certain resource, for certain tools, and other users who have totally different credentials want to use them also. So we have to find measures that's able to start them and read them with a effort to teach them. We want, of course, to use the incarnation database to have the information about the available tool per resource, and integration of IRAPs with Unicore. That was because of the distributed data management. So what we've accomplished is at the moment that the Science Gateway runs a PRACE certificate I can easily create on XSEDE site. And this PRACE certificate is shaped in a JPS command line, and this I can upload into the Mosquit US. For instance, we named it Mosquit US, but we also integrate PRACE there, so we will rename it again. And so we create now from this proxy certificate directly a summary version that can be used for the jobs. And if you have a look at the docking workflow, it's really a complex workflow with preparing religions, preparing the receptors, and the users don't want to on each of the boxes to change the properties. So we them with creating their workflows more usable. And first workflows we imported for the quantum chemistry community in the S instance. And what is the first workflow is a meta workflow, and other ones do that, except for the hello. The NWChem workflows are small workflows which are integrated in the first one, so that it looks like this. It makes it much easier and possible for the user to work with them. The ongoing work at the moment is that we can discuss that maybe after talk or later, coming back to that. So I have to apply some XSEDE rules for Science Gateways, because we talked about that there should be one Science Gateway certificate. How to submit really from a Science Gateway jobs. And they're not so suitable for Mosquit features, especially if you look at distributed data management. So the users have their own user space, and they don't have their own user space for their data anymore. As I mentioned, they would share data, 70% of the users, but they don't have the results that really can protect their data. They wouldn't like to go for the Science Gateway. Another invitation what's going on at the moment is to have an automatic authentication in library with the XSEDE account, so that the user doesn't have to fill in his email address anymore. To use the incarnation database to have all the tools available in the list about that the user has this available. We are supporting more workflows for GROX and NWChem. The work on the integration started. The plasma physics side, this is PyCon GPU is the first scalable GPU cluster implementation. So it's really with clusters in the background, MPI, and then the CUDA toolkit. They got the prize with Jordan Bell finalist in 2013. And for international collaborations, yeah, the international GPU sources would be ideal because they have really fantastic scalability up to 10,000 GPUs. They have proven that once. Of course, they don't have always 10,000 GPUs available. And not each of their use cases needs so many. But also up to 1,000 or 500 would be fantastic for the collaborators in this field. I like this picture very much because it shows one of their experiments. And also plasma after shooting with laser on aluminium foil. And they set up this experiment. They did first the simulations, how to set up the best way. They really have the best starting parameters they can have a look at. So this was to have access to XSEDE and PRACE Unicore GPU resources. Unicore workflows for easing the use of the software. So software is easy to install, it's open source. But how to start with parameters, what is the best to pre-get data, to pre-process data before doing it. And here we are working on the authentication via the XSEDE account. We would take over the work we have done from scratch. We are working with the researchers themselves on creation of the workflows, which use cases that they can create simple workflows at starting point for collaborators. And we want to use Unicore for the GPU resources. So yeah, I had some challenges here. Maybe I'm too honest with this slide, but the time on my side, so I'm the PI of the project, was a little bit constrained, and so that's a general problem in academia with projects which have no financial means. Still to emphasize that we are collaborating with XSEDE and PRACE was really great. Will be further on great. I had some time problems in between being in this situation, having not yet a team, writing proposals. But I don't want to whine. It's only therefore we had some time constraints in the project. Policies on access to XSEDE and PRACE. So we should maybe really discuss this topic with the Science Gateway certificate. So we need the grid and also for the high GPU other methods there. And Unicore GPU resources, it seems like that Unicore in XSEDE at least has not so many GPU resources behind. So resources are there, they're fantastic, but not reachable by Unicore. So the idea from the project was if PRACE would be in favor of that, maybe we could write together a grant for use cases to get NSF funding. Financial means are available to do more use cases for both communities. That would be fantastic. That's for your attention. Any questions?
Sandra, thank you very much. Any questions from folks on the line for Sandra?
Heidi, I have a question. Shabazz here.
Yes.
Firstly, thanks, Sandra, for a very nice talk on Unicore. My question is about what technology or what kind of workflow framework you're using for this Science Gateway. Unicore's core workflow engine, or you have your own workflow engine? The gateway?
That WC Grade and GU are developed from the MPS Starkey in Budapest. And we are using that workflow technology. And the nice thing is that you can really distribute each job of a workflow to different resources. makes it very nice if you have the distributed data management with Unicore, for example, integrated. The data between jobs is then not transferred to the different locations, but accessed via the distributed data management tool.
Okay. And my second question is, so what is the stopper for having Unicore with GPUs? I think it's not an issue. So we have PRACE sites which has GPUs with Unicore exporting and exposing these the HPC site resources and capabilities.
No technical issue. There's no technical issue. It was only that some, or let's say the GPU resources we talked XSEDE are not available via Unicore, but widely used also for other projects. Don't get me wrong there. It was only for this project I couldn't use them because it was not Unicore.
Okay. Got it. Thank you.
Yeah, I was going to ask, I know Stampede's got some GPUs. Which machines in XSEDE were you using, Sandra? Right, in general, there's a shortage of GPUs in XSEDE, yes.
No, it's not a shortage. So Stampede is great. I use it for another project. I only cannot use the GPUs for Unicore. Stampede.
Okay, we'll have to check on that. Yeah.
Yeah, so Nancy, I think there's some special configurations you have to do on the back end to those GPUs to be available via Unicore. Check with the task folk to see if that's been done.
Great. This is exactly the sorts of things these interoperability projects were uncover. So very nice.
Yeah.
Sandra, thanks for a very nice talk. I think I'm partial to gateways, but I think they provide a nice interface as far as kind of simplifying the underlying complexity of using multiple sites. And one of my questions was going to be Unicore is very much newer on XSEDE resources than it is on the PRACE resources, I would say. And did you run into any issues? But I think that's kind of all come up. So those were exactly some of the things that we wanted to learn.
Oh, I bet it would have been to say if I would have, asked often whether we could do that. I'm still continuing this work to yeah.
Good, that'll solve. Yeah, go ahead, Tabitha.
Sorry, I was just going to say, Sandra, if you have any trouble with any of the Unicore sites, just loop me and I'll try to, it's on the XSEDE and try to smooth things out.
I only mentioned it at the moment because I haven't tested now the GPU code yet on these.
Yeah.
But it was not a real technology problem.
Okay.
So yeah.
No problem. Thanks.
Yeah, that's good. This will make things function better for other users as Unicore gets more wide use in XSEDE. So thank you very much. I think with this we've run a bit over time. I know we originally were thinking about 30-minute presentations per team. We thought, oh, gee, that sounds a little bit long. Let's go with 20, but it's turned out to be more like 30 anyway. So thank you for everyone for sticking with this. I think it's been a really interesting session. I want to especially encourage our speakers, the folks DeLon, Morris, and Sandra, to work with Tabitha on the XSEDE 15 paper. Thanks for the very good idea to write such a thing, Morris. And we'll make sure to loop Shantanu in since he's had to leave the call. But we'll be actively. Ralph Roski's also sends his apologies. He had some connection troubles this morning, and then had a meeting conflict, so he would have liked to be here also. So I'm sure the PRACE and XSEDE teams will be actively discussing kind of next steps. I know that we would both like to do more in this area. I want Florian and Jules, if you have anything you'd like to add, if anyone else has any questions for our speakers.
Yes, Nancy, I would like also to thank all the speakers and participants of this webinar of today. It was nice to see the results of the PRACE XSEDE joint call, and I had the impression that the selected project really paved the way for future collaborations. And I'm convinced that the project enabled a better use of the PRACE and XSEDE resources.
Nancy, it's Tal, and I'd also like to take the opportunity to thank the speakers who pointed out the subtle but underlying role of OGF-based standards in their work. It's not the sexiest thing to talk about, so we always appreciate seeing it. Please keep in mind that there is OGF 44 in May 21 and 22 as part of the EI Spring Conference in London. So we hope to bring a lot of groups together to continue this discussion about interoperability. And we look forward to any other opportunities to meetings that are helpful to interoperability.
Great. Thank you very much, everyone. I think that concludes our webinar, Florian. Thank you for getting the WebEx. I thought it worked well.
Yes, I was also very satisfied. Thank you all. Have a nice weekend.
Yes, you too.
Okay. Bye.